All right, well, today I want to talk about something different. Let me get a share screen going here. I want to talk about stars. This is based on a database of stars. It's available at this website, and it's called the HYG database. It's based on three major catalogs: Hipparcos, Yale Bright Star, and uh, Gliese catalog of nearby stars. Um, Hipparcos is probably the best for stellar positions, particularly measurements of parallax, which is how you measure distance to stars. Um, Yale Bright Star Catalog is essentially all the naked eye stars, the ones that you can see in the night. And Gliese is uh, uh, catalogs all the stars within 75 light years of the sun. And consequently, it picks up a lot of faint stars that aren't in the other catalogs. And the name HYG comes from those three uh, database or three different databases. So there's almost 120,000 stars in these databases. Um, and my goal here is going to be to display them. So the fields from the database that I use, there's a lot of them, and I didn't bother with all of them. But a few stars have names. About 140 stars have names. Things like Deneb, Antares, and Betelgeuse, named stars. I also use the absolute magnitude, which is a measure of how bright a star is. It's a little difficult to use because it's a logarithmic scale where each integer step is 2.5 times brighter than the next one before. And you can read about that if you want to find out why they did that thing. One of the primary things I use is the Morgan-Keenan classification system. In the database, they have what type of star they are, and different star types are O, B, A, F, G, K, and M. Those are the main sequence. In this sequence, the O types are the hottest and hence bluest, and the M types are the coolest and hence reddest. And I'm going to use that to color my stars. There are also some obscure types, L, T, and D. These are all dwarfs. So of course, position is the key here. And the database actually has X, Y, and Z Cartesian coordinate systems in a system based on the coordinates as seen from the Earth. So actually, the position of a Sol, the star that corresponds to our sun, is not a 0, 0, 0. It's offset a little bit because the coordinate system is geocentric. We are at the center of this little universe. I haven't used it very much, but it also has an estimate of the velocity of the stars. So how they're moving in the sky, and this is really tricky. It's determined from proper motion and radial velocity, and radial velocity is relatively easy, but proper motion is very, very hard. One I did use a lot was the luminosity, which is a linear measure of absolute brightness of a star, with our sun being 1. So this was a really good parameter to use to kind of get an estimate of the size of a star, because the kind of first order, the bigger it is, the brighter it is, the more light it gives off. It has a bigger surface area, so it gives off more light. Here's the spectral types. The O that are the hottest, bluest stars, and the M's, L, and T's, these are dwarfs, that are the reddest stars. And in between, we have G's, F's, and so forth. I believe the sun is a G. Just for comparison, these are kind of rough sizes of different classes of stars. So the M's are small. Here's a G, that's what the sun is. And it goes on to these giant stars, the B and O. And these stars can get really big, like 1,000,000 times the size of the sun. So in dealing with any database, you're of course dealing with the format. The HGY catalog is in CVS format. This is comma separated. And as such, it's going to require some manipulation to get it into a format that Unity likes. We're going to use the stream reader, and it likes fixed format fields. I wrote the pre-processing program in Fortran. Fortran likes the CVS format, the comma separated. It handles it without any futzing around. So I just read these things in using character data, which is the Fortran version of the string. I read them all in as characters because some of the data is numerical and some of it is text, things like the proper names and the classification, those are text. So I just read them all in as character data. And then I would parse them out of the character data into numerical data if I needed to. And the trick in Fortran is, here's the character data X, and I'm reading from that character data the real number X1. Reals are equivalent of C# floats. And then for Unity, I write this all out in a fixed format with 18 slots for each field. And F18.7 puts 7 digits to the right of the decimal for a floating point number, like a real. And the text, the proper name, and the spectral class, I output just as characters in an A18 format. So all of my fields here, my 10 different fields, are 18 slots wide each. One other issue was the conversion of that MK classification system to numerical values. In Unity, I wanted to be able to use that value to select a color from a gradient. With the MK classifications, you get the letter G or M, and then a second number that goes from 1 to 9 that spaces along the scale of the classification. So a G5 is halfway between a G and an F, and G9 is almost an F. Fortran, again, gives access to individual elements of the character data type. So here I'm extracting from Spectrum, which has 2 slots, beginning at the first and ending at the first, so that's 1 slot, and then S2 is beginning at the second and ending at the second, so that's the second slot. So I'm breaking that spectrum into 2 pieces, and then I have some if and else that parses the categories. For the T's, I add 1, for the L's, I add 2, for the M's, I add 3, and so forth. And then for the second part of it, the numerical part, I add a 0.1 to correspond to the different pieces. So a G5 ends up returning the real value of 5.5, which in Unity I can use divided by 10 to select a color out of a gradient. The gradients go from 0 to 1, and so selecting at 0.55 is going to give me some color right in around here, yellow. So in Unity, reading the data, I'm going to use a stream reader. This requires adding the I/O usings up at the top somewhere. I've got a exposed variable for the file name and the extension .txt, which is what I wrote in Fortran. Here's where I specifies the size of the format, 18 slots. I'm reading until I hit the end of stream. I'm reading a whole line. And then I'm breaking it up with substring. This is where it starts, and this is how many characters to take. Format is 18. Then the next word is offset by a format amount. So I'm actually reading 1 through 10 words in here. And then to convert back from the string type to the floating point type, I have the float parse command that takes that string and turns it into a float. And I do this for all the things that I need. I form a distance that's just x squared, y squared, z squared, square rooted. I've got a size, well, a position. I'm scaling that by something to allow me to adjust the size of my world. My velocity, luminosity, size, spectrum. Here's where I do the 0.1 to make that 5.5 into a 0.55, star name and star spectra, all of that for display. Instantiating all the stars, I've got this base and instantiating all the stars. I'm just instantiating them at position with identity rotation. I'm giving them a name that comes from their star name. I'm giving them a tag star, which I'll use later in another program. And I'm setting its color here with the luminosity scaled by that base scale. Here I'm extracting it from the color gradient, evaluate at spectrum I, gives me a color sample, and I just assign the material that color. All very straightforward. One thing I didn't mention was the fact that star sizes vary over literally 12 orders of magnitude. There are dwarf stars the size of the Earth, which is about 10 to the minus 6 of the sun. And there are hypergiants that are 1,000,000 times, 10 to the 6 times bigger than the sun. So displaying actual sizes was not an option. And I instead chose a logarithmic scale. Logarithmic scales kind of collapse down these big orders of magnitude scales into something a lot smaller, you know, about log base 2. I use log base 10. To have a size that makes any sense, you want it to be positive. So I shifted all the luminosities so that the smallest star had a luminosity of 0. So I found the minimum luminosity and shifted them. Then I added 10 to it. 10 means that when I take the log of that 10, the base 10 logarithm of 10 is 1. So my smallest star then is going to have a size of 1. The Earth is going to have a size of log 11, since the Sol is going to have a log 11 size on up to the biggest stars that are 1,000,000 or so times bigger. They'll be roughly 10 or 12 for the very biggest stars. Most of them don't get much bigger than 6. But anyway, the sizes that you'll see when this thing runs are logarithmic sizes, not actual sizes. If they were actual sizes, the big stars fill the whole universe. Finally, of course, a mechanism to switch which star I'm looking at. I put this on a free look camera rig called Looker script. And working with the standard assets cameras is a little tricky because they're all built on top of an abstract target follower class that is the base class of all of the camera scripts. So we have to use using standard assets cameras to have access to this class instead of using the free look at camera rig script. We use the abstract target follower type. This is going to be the camera that follows. Well, actually, it's the script on the rig here that has the target. That's what I'm trying to access, is the target. One thing I'll show you later, I'm also accessing my data reader. This is because in my UI, I want to show the name and characteristics of the star that we are looking at. So that information is over on the reader script. various arrays for the things that we're going to handle here. And I remember I set the stars tag to be star, and so now I can find all these objects with tag star, extract from stars the transform, the position, uh, uh, well, making the arrays here. Uh, I'll load the arrays um, from that those star game objects, extract the transform, the position, the name, and here's some that I'm getting from the reader, from the reader script that's controlling, instantiating all the stars. It has an exposed variable for the star spectra and the star size, and so I can just reach over and grab them from the other script. Here's where I'm accessing my free look camera. I'm getting component abstract target follower and setting the target to be the transform of the chosen star index, the one that I'm looking at. To make it more obvious which one I was looking at, I put a light out there, and my light is a public variable in this script, and I just put it at the star position, and I've got this little set light on star, which we'll see the set light on star just grabs the star's material color and sets the light to have the same color as the star. It also sets the size to correspond to the star size. And here's that trick I'm doing with 10 plus the star size, log 10 of that. And I made it 5 times bigger so that it makes a halo around the star. And I also made the range equal to the light size because this is what scales the size of the halo, which had to be, the halo had to be turned on the light. We have to have the halo turned on. I skipped the update here. Update, all it's doing is watching for various key codes that are going to increment or decrement the star index. Before I read these in Fortran, I sorted them by distance. So the first star is our sun, the Sol, and it progresses out through the database as you go further and further from the sun. So an L key steps forward in that list. So starting at 0, you go 1, 2, 3, and a K steps backwards. So if I do a K, it'll go to the furthest star if we step from the sun, and R just resets it back to the sun. And I think that's all there is to it. I've got 4 main scenes. There's some n-body ones that I won't talk about here. We'll talk about n-body another time. I have the named stars that has the 143 named stars. This is controlled by the K and L keys. They're sorted by distance. In the database, there were a number of Pharah stars. These were all a uniform distance away, 100,000 parsecs. And I think this was basically because they are so far away that their distances are not well known. What the guy running the database did was just kind of project them onto a sphere that was far away. And I extracted them out to separate from the stars that we know where they are. There were around 10,000 of those. The database that's fun is the All Stars database. This has 109,000 stars. I left out the Pharah stars. And of course, in addition to the look at individual stars method, there's also a fly-through so that you can fly around in the world. So let me show you what this looks like. These are the named stars. So here we are looking at the sun. What I think is interesting here is if I turn around like this, uh, you can see there's the Big Dipper over there. Uh, Here's the Big Dipper. Uh, and it only looks like the Big Dipper when we're looking at it exactly from the point of view of the Earth. Uh, uh, if I, because those stars are not uniform distance away. There's something wrong with my camera here. So if I step forward through these, this now goes to Proxima Centauri, Rigel, Barnard's star. This is one they recently found a planet around. Landy, Sirius, the big bright uh, star. Uh, it's also fairly big. Notice these are really tiny stars. This is a big 22. And as we go on out through here, uh, we look at different stars all the way out. Um, Resetting back to 0 and now going K through this. Now we're out at the faraway stars, and we only see the faraway stars if they're really bright. So you can see this one's 37,000 times bigger than the sun. Uh, uh, 67,000 times bigger than the sun. It's a B. One that's kind of famous is Betelgeuse. That's the one that's nearby that supposedly is on the verge of going supernova, uh, uh, and it's out there quite a ways. I'm going to pause sharing here for a second, and I'm going to pause recording, and I'm going to go fix the interface. So I'll be back. All right, I fixed the. I fixed it. Hold on. The other share screen. So here now, this is the proper way this works. With the mouse, I can kind of rotate it around and jump to the various stars. So out here at Hatsaya, where's the center? So there's looking back at the center of my world. So those are the named stars. Here are the Pharah Stars. The Pharah Stars, you can actually kind of see the Milky Way here in the Pharah Stars, this band of blue. But if I step out, what I find is these stars are all on a big sphere. They're all exactly the same distance, 100,000 parsecs, which corresponds to over 300,000 light years away. So these are all far, far away stars. And a lot of them are very big because the only reason we can see them is that they're far, far away. I mean, is that they're very bright. So these are all the big ones. There's one that's 2.6 million times the size of the sun, big star. And of course, the one that I was aiming for, this is the All Stars. And this is 100,000, almost 110,000 stars. So this is, of course, where one had to be fairly efficient about materials and so forth. I accidentally left a collider on the star objects, and even though the collider was disabled, just its mere presence on the prefab that I made the stars out of, that disabled collider, knocked the frame rate down to 2. So one must be careful here. And so here we are looking at the center of our universe, or our galaxy actually. And as I step out here, I'm stepping out to all these little stars that are close in. Notice a lot of these are very small, these nearby ones. If I go out the other way, if I go out the other way to the faraway stars, this is a no-name star somewhere out at, far in the distance. It has a size 80 times the sun. There you can see the center back there, all the 100,000 stars that are all closer than it. And here we go, we'll zoom back in to the center of our uh, galaxy. And this, of course, is not all the stars in the galaxy. This is only the stars within a certain distance of the Earth. These are the visible stars, the stars that you can actually see in the sky. And there are many more that we can't see. And finally, a fly-through version of this. This is just a very simple uh, fly-through that uses the arrow keys, or W, A, S, and D, to rotate, and it's a pitch and yaw type interface. Up and down arrow keys to pitch, and right and left arrow keys to yaw. And I think the X and Z are the throttle that accelerates or decelerates. And I think the C key sets it to 0. So I can now fly through my galaxy of stars. And all that's pretty cool. And I'll stop there. This was a fun exercise in displaying lots and lots of things, uh, and stressing out the system. So I'll stop the sharing here, and I'll end the recording, and I'll see you all in class. Bye.